So I can have one batch coming in, and then the ALab OS even analyzes if, for example, let's say you have a reaction, and then some other scientist comes with a different reaction, and sees that the temperature of the furnace will be the same for both of you, and the profile is the same. So then this software is going to try to combine your samples with the samples from the other scientist.
That is so smart.
It's really cool. So all these tasks happen at the same time. And the process, of course, are parallel. So I can have new samples being prepared while I'm recovering the powder here to prepare for the analysis, while other ones are being analyzed right now. So it keeps going. So we can have people constantly having new experiments being inserted, and the lab is going to manage everything, calling us from time to time just to clean some things.
Welcome to Discovery Engines, a podcast about the people and platforms who are accelerating scientific discovery. When I first started my journey, one of the first places that caught my eye and sparked my imagination was a place called the A-Lab in Berkeley, California. This lab, built by the Lawrence Berkeley National Lab, combined machine learning and autonomous robots to do really interesting new types of material science research and discovery, especially in the area of new batteries. Imagine a future where, while a scientist slept, an autonomous scientist could continue some of the research that they were doing overnight and present the scientist with new results in the morning. Or imagine one of these systems working alongside a scientist and helping her or him with some of the tedious work that one has to do when doing really novel, groundbreaking research, and allowing the human scientist to focus on some of the more fun or creative aspects of their work. Well, you can imagine my excitement when, over the last couple of weeks, I had an opportunity to visit this lab myself in real life and get a tour by one of the very engineers who has been working to bring it to life. My guide and interview partner on this episode is David Milsted, a postdoctoral researcher who has spent the last 3 years at the A-Lab as part of the team that's been designing it and bringing it to life. In my conversation with David, we covered his journey from wood science to lab automation in the materials space, an overview of how materials are typically discovered and created and how the A-Lab goes about it, how the various instruments in the lab are orchestrated so that they can work well together, how David and his team work as part of a unique academic and government partnership between the Department of Energy and UC Berkeley, the future of materials characterization via microscopy, and last but not least, a full lab tour, including all of the major components that need to come together in order for this lab to work, along with a discussion about the various vendors and suppliers who are also part of the larger lab's ecosystem. For those of you interested in getting a sneak peek into how the batteries that are powering your next device or maybe your next car might be developed, come join me for a tour and a discussion of the A-Lab. Let's go. David Milsted, welcome to Discovery Engines. Glad to have you here.
Thank you.
Absolutely. So we met a couple of months ago. You delivered a really interesting talk at an event in the Bay Area around automating materials discovery. And I was excited to learn about what you're doing and also know about your association with the A-Lab, which I had heard about. And so I asked you if you would jump on this Discovery Engines podcast with me. You not only graciously agreed, but invited me to actually come down and visit you at the A-Lab, where we're here today in the foothills, or in the hills, I would say, not
Yes.
the foothills, the full hills of Berkeley, up in the clouds. You can see the mist sort of burning off right now. We'll be getting some cool views. So appreciate you having me here.
Oh, you're welcome.
Well, I had heard of the Lawrence Berkeley National Lab, and I did some research on Wikipedia, and there's some fun facts that I wanted to make sure that folks knew about this lab. And then as you listen to these, if there's something that I'm missing or that you're particularly excited about that folks should know about just this larger facility, please let us know. So it's one of 17 Department of Energy national labs, founded in 1931 by Ernest Lawrence, with an initial focus on physics research around something called the cyclotron.
Oh, that's right.
Yeah, a particle accelerator. You have 6 areas of research at the lab: computing sciences, physical sciences, earth and environmental sciences, biosciences, energy sciences, and energy technologies. You claim 16 Nobel laureates, have a budget of about $1.5 billion, and are managed by the University of California. Whew. Did I miss anything?
No, I think it's complete.
Yeah? Okay. So you work in a pretty incredible place, I think it's fair to say. I'd love to talk more about the lab in a minute, but I'd actually love to start off by chatting more about you and your experience. So you yourself have a Bachelor in Industrial Engineering from the Federal University of Paraná in Brazil.
Yes.
You then got a PhD at Mississippi State University. You're now a postdoctoral researcher at the Lawrence Berkeley Lab for the last 3 years or so, where you've been building an autonomous lab to make and test materials, aka material synthesis and characterization, all of which started, as I understand, with maybe an interest in wood and all the way back in Brazil. So I'm curious, starting off from the beginning, like what inspired your journey into this field, into engineering, that eventually brought you into this autonomous materials and labs space?
Well, maybe I can start with like 2012 when I was having my first automation classes. And during that time, the professor was just teaching about the automation principles, very basic stuff. And I found it like amazing. I was in love at the first sight. Then I asked him if he had any student that would, that was working with him to do like any scientific initiation, that's how we say in Portuguese, where you just go to the lab, work with the professor, and then get into science slowly, like maybe you can start with experiments, then you go more into publishing articles, normal science. So, but like the baby steps. And then he, for my surprise, he said, no, I don't have anyone here that's very interested in automation. So my undergrad is like kind of double major in the US. So it's mandatory to do the wood science and the industrial engineering. So industrial engineering in my case would be more connected. Here in the US, a bit more on the mechatronics side. So then people in my major tend to go more in wood. And then I was like, no, I think I want to go that way. So then I got a lot into automation. Then my professor showed me some ideas he had. And I remember I told him, Professor Ivan, he's probably going to watch this. I told him, Professor, don't tell anyone about this. I want to make this my undergrad thesis project. So then I started studying deeply, more into the programming side, then into electronics fabrication. So my major could cover slightly, but broadly. But then I had to go deeper into that. And then I got some donations from a company I was interning, so they gave me a lot of nice equipment to work with. And then I came up with a machine to automatically study wood samples. And then I had to write a software in C# to be collecting all this data and then transforming into useful data. So for continuous monitoring, that was the purpose, to do analysis that would go analyzing how this wood would shrink or swell in different conditions. And then you could, because many times people just go in 3 or 4 points in the curve and then extrapolate the data in between. And we were like, what if we tried to go in every single point of the curve and measure instead of interpolating these results? That was the purpose, but then we started to have more capabilities. And then I presented that as my undergrad thesis, and the committee told me, you have to try to patent this. So then the university there gave me all the support they could, but they haven't, at least at that time, they didn't have any patent attorneys. So, and they wouldn't pay for any fee too, but they said, we can give you the training, so I can tell you where you get this training. And then that's how I learned for a year about how the patent process works, how to write patents, and also how to recover information from patents. They call this the technology recovery, and then I wrote a patent. We deposited the end of 2017, and then in December of 2023, I got the patent that I wrote myself, but which was a very big surprise. I didn't know it would work. So that's the patent I have for this device.
Wow. So they said, we're not going to give you a patent attorney, but we can make you a patent attorney.
A very basic one, but it worked.
That's amazing. Can you tell me more? So you said, your initial focus was around wood samples and analyzing them. What I love about that is when I think about, materials discovery, often I think our minds go into these exotic materials, right? But wood is so elemental. And can you tell us more about why that was essentially an important field of study, maybe particularly in Brazil, and B, like what interested you about specifically wood as an element?
So the major itself was in wood science. So it was, if you go, technically the name of the major is Timber Industrial Engineering. So it was mandatory to do both, which make it very hard. Then the wood is a biomaterial that throughout history, this is what I like to tell people why wood science matters a lot. So people are like, oh, trees are just there, they're boring, let's burn them. And then later, okay, that was a bad idea. Let's go and fix that. But then later we start to realize how important it is to go back to sustainable materials. And wood is a material that would take, carbon dioxide from air and transform into a structure. So it's the true carbon cycle. It's very present in wood in a way that we can use the material and goes back to nature, but then go back to material and keep going back and forth. So if we master that, we can learn really well how to challenge current things that are happening in our planet right now. So wood is very important in that sense, and like any scientific field, we have to explore more and learn more about it. So this is why we have the wood science as a distinct field, and wood science was bigger in the past. Now it's not that famous. Many people don't know that we actually have this field in wood science, but I'm pretty sure that the current needs are going to make this very relevant again. Like any other engineering, like any other science, there's the high point, and sometimes almost disappeared and go back again. So I think that's normal.
Very cool. Well, I think being in Berkeley and in Northern California, I remember being here a few years ago, and the fires in this area were so ferocious that I was working at a coffee shop, and there was literally ash falling down on my computer, and you could see a layer of ash on the cars in the street. Wow. So I think having a deeper understanding of the cycle that, I guess trees take and the nature of wood, maybe even sampling the wood as it's growing to understand its flammability characteristics and so forth, all of those feel increasingly important.
That's right. What got my interest in wood is because the tree is the living being. But once you cut the tree, then you have wood, right? That's where the moment where it changes from one to the other. And because it was a biological being, even after it's not alive anymore, it keeps reacting with the environment. So what I was studying was exactly how the water behaves in wood and what are the effects. So for example, you probably know that in the summer here where we have more rains, maybe not in California, but in other places where you have more rain, the doors or the windows, they are harder, or even sometimes even in your own home, like during the rainy season, you feel that some things, they change the dimensions. So the door is harder to close, the window is harder to open or close. And that happens because the wood is reacting to the environment and is swelling. And then once it's dry again, it loses this water. So this effect was one thing that I found fascinating in how the water molecules, they bond to the cellulose and make this material to swell or shrink. And that effect is where it was my biggest interest at that time.
So you had a double major at your university. You then patented your own invention. What happened next in your journey that took you from that university to here at Berkeley?
So I think it was in 2016 when Mississippi State University sent a delegation to my university, and luckily at that time we didn't have any classes, so I could attend to their presentation. And they were inviting people from my major to come to the US to study. Of course, you have to do the application and all this the normal steps. But they were inviting people because wood science is not that known. And my university had, it's like at that time, I think they had only 3 universities in Brazil that were teaching this major. So they visited them all. They're like, hey, look, we can have you here for graduate school. That's when I applied in the end of 2017, got here in 2018, and then started studying again wood. And then I thought I would be leaving automation behind, even though it's my dream. I was like, okay, it seems that wood science is the way for my career. But then my professor knew about the machine, and he was like, can we have a machine like that here with us? And I said, well, I can try to build one, but can I make it maybe better? That's how I then got again into automation, and I tried to make the machine bigger with more capabilities. So I tried to put some like IoT capabilities and remote monitoring control. And also I developed my own thermal hygrometer. So then I could learn more about this part of like the sensor development. And I was not very happy with the results until I presented in a conference, and a professor from Oregon came after my presentation and said, your sensor is really good for the price you built it. I think it was about $50, and we got like 8% of precision. And he was saying that because that value was like not interpolation based on other things, but an actual measurement of the property in the air. He was saying that any sensor better than mine would be about $2,000. So then I was very happy with that. And then I stopped saying that it was not that good, because then I knew it was good.
Wow. So there's this intermarriage of wood and automation that keeps on cropping up in your career journey.
Yes.
That took you to Mississippi State. Okay. And then from there, how did you land at the Lawrence Berkeley National Lab?
So I was about to graduate. It was the time to look for some jobs. And I applied for many jobs in the wood science, of course. But then it was one night I was talking to my wife, and I saw this perfect position in Berkeley Lab that was specifically in automating the research, but it was in material science. So I talked to her and I was like, I feel this position was made for me. This is exactly what I like to do. I love wood science, don't get me wrong, but I love more automation. So then that was the only job I applied that was not in wood science. And then I was accepted here. Then I was like, yeah, I'm going to pursue this. Now is the time. It came.
What do you think they saw about your experience that caught their eye and made them want you here as part of the lab?
So after I think I was here for at least 1.5 years, and then one of the persons that was interviewing me, she was about to leave the group, and then she was like, okay, now I'm going to tell you a secret about your interview. So one thing I did on that interview was to show a video. And that video, I made on SketchUp, I think in one afternoon, just to show to my professor what I was trying to do as my next machine. And the idea was to show a device that could, keep remotely monitoring the wood samples and doing constant analysis, but in a different way than the machine I made. So it's still the same purpose, same idea, but in a totally different shape with different methods. So I made that video to convey the information, because my professor, when I met him, he was 88 years old. So, and he was still working, normally. then I had to, because we have this gap in communication, right? I had to show something that I knew he would understand. So I prepared a video. Then I saved the video for later. He said that that was too complex, so we went to like some less steps of complexity. But I showed that video on the interview to show like how I think, you know. So we had this issue, and then this is what I believe can solve the issue. And she said that that video is what got me the job, because they knew from that video that, you know, the way I think, the way I try to even convey information, for them this was very important, because with that they understood what I can do. And then they're like, yeah, he said later when they were discussing, she said, you know, the guy that showed the video, he's the guy we need. So the video was that important, and if she never told me, I would never know. So I'm very thankful that she told me that this video was so important.
That's what I, you know, am inspired by in that story is, you know, I imagine, and correct me if I'm wrong, but in your education up until then, you hadn't gotten a lot of, you know, video creation training or communications training as an engineer.
Yes.
And ultimately, that's also what really helped you stand out. And I imagine not just as an interviewee, but as having a capability that's really important in a team-based environment, where you have to communicate your skills to folks who maybe don't know nothing about automation, but know a ton about material science.
That's right.
And so forth. And so I hope other folks take note of that, because I think that is a superpower that one can build.
Yeah, when I had one presentation in the group here, the internal group presentation, one of the things I focus when I talk to them is exactly the communication side, on how can you convey your idea to someone that has nothing to do with your field. So then there's the classic like that, an image is worth 1,000 words, right? And then I was like, but how about a video? This is what I try to tell people to consider when they are trying to convey a complex idea. Maybe a video, you know, and SketchUp, at least at that time, was totally free, not that hard to use, and was enough to show in a simple way, a complex concept.
That's awesome. So I'm curious, this is more of a personal question. Curious to get your reflection on it. So I myself am an immigrant here. I came here as a kid, originally from Tunisia. And you know, I have seen some of the challenges, but also some of the opportunities as somebody who came from a different culture and is working in America, to have a unique perspective to the work that I do with my colleagues. I'm curious, you know, when you reflect on your experience having worked as a scientist in, you know, Mississippi, in Brazil, now in, you know, Berkeley and in California, like what has your own, I guess, cultural experience brought to you as a scientist, or what have you learned from working across those different cultures?
Wow, it's a very rich experience, I would say, you know. Wow, this goes back like to when I was 13 and I read a book about studying abroad. And at that age I was like, wow, this is an experience I want, you know. So when people say that traveling opens your mind, that's a real thing. And coming here, you know, and even from Mississippi to California, we can see a lot of different cultural aspects. And I think even the weather changes a lot of things on the behavior of people, and then we learn a lot on that. I also have been in, I think maybe I'm going a bit far on this question, but you asked a personal question.
Yeah.
So I have been in Wisconsin for a winter, and this is how I explain to Brazilians what is to live in the US. I tell them, you know, when you watch the cartoons and you see like people going and doing like digging a hole in the ice to do ice fishing, they're like, yeah, so that is a real thing. You can actually do that, and I did it. So that's something, to me, was just a fantasy, just a cartoon, you know. Then I came here and people actually do that. So being in contact with old cartoons, you know, Hanna-Barbera, Warner Brothers, Bugs Bunny, and all these people. You know, the hunting season, we don't have hunting in Brazil that way, you know, the season. So season is open, season is closed, and all these things. It's actually a real thing. So all of these are are things that when I came here and I saw it the first time, was amazing. I was just like, wow. I remember I have one of my friends from Mississippi State, and he was this American friend showing me like, hey, let me show you what is to live in the US. And he's the one that invited me to go with him for a Christmas time in Wisconsin. So I was with his family doing all these nice activities. They could taste, a lot of the American culture. And I don't know, I think the best way I can explain is that it's absurdly rich. And this motivates us to try to not only learn more, right, but also to bring what we can offer from our background. So in many senses, it's been very rich and tasty experience.
Yeah, awesome. Well, let's go into materials. So, your work over the last few years has been in automating materials discovery. On your LinkedIn, I saw you talk about through the use of SolidWorks, 3D modeling and printing and microcontrollers, I'm developing equipment for specific laboratory tasks that will be used together with robotic solutions to automate all of the scientists' artisanal work. I love that term, artisanal work. Maybe gets back to the woodworking sort of story. So not being a material science myself, and I know you are not either, so maybe we'll learn together here, but I was trying to think of like how might I simplify this so that I understand the process of coming up with a new material. And so the kind of example that I'd like to offer is, let's say that I work for a large airplane engine manufacturer like General Electric, GE. Mm-hmm. I know that they, when I'm flying from California back home on the East Coast, right, I'm flying in these Boeing planes, they've got a GE engine strapped to them, or hopefully more than one, a couple. Yeah. And I'm thinking, okay, well, I know that airplanes use a lot of fuel, so it'd be helpful for them to be lighter, and that will help them use less fuel, which is good for their bottom line, also good for the environment. And so let's say that I'm at GE and I want to create some new alloy or metal for the turbines in that engine. So the steps that I might go through, first I might define the requirements for that metal. And so that might be things like, what is the tensile strength that I need for these turbines? What is their resistance to different temperature fluctuations, to corrosion when they're sitting out and it's hailing or sleeting outside? I then, as a next step, might then take an educated guess based off of my experience as a material scientist, based off of research that I might see around what are some of the different, essentially, metals. So essentially elements that I can combine from the periodic table to create certain types of metals that might have those kinds of properties. What I as I understand it, ultimately those are formed into crystals, lattices, and grains. Those are kind of the elemental structures of metals. So what might create lattices, grains, and structures of that sort that have those properties. The next step is I might then try to make that material. So I think in the material science world it's called synthesis.
Yes.
And it involves processes like heating, applying pressure, cooling those kinds of metals, or those substances to create that alloy. Then I want to test to make sure that what I actually created was what I wanted to create. So that's what we get into this process of characterization.
Yes.
And it sounds like one popular way is like X-ray diffraction, or XR.
Mm-hmm. XRD.
XRD, okay. And so once I've done some X-ray diffraction, I might then go into performance testing, which is saying, okay, I've made what I think I wanted to make. Now let's actually put it in an environment and apply these kinds of performance criteria. And if it's successful, awesome. If not, which is probably going to be the case, at least the first few times,
yes,
I go back to the drawing board and continue to test new hypotheses. So that's kind of like 5 steps to go from sort of a certain requirement to the potential thing that I've created.
Yes.
Does that feel broad picture like the right story?
Yes, it feels correct based on what I see from my coworkers here. They do all this amazing work.
Okay, cool. So as I reflect on that process, like one big challenge that I see in that process is in step 2, right, taking that educated guess of, what are the materials that I want to create that are going to have these performance requirements. There's an infinite number of ways in which I can combine these different elements from the periodic table. And, I'm not really sure where to start. So one initiative that have seen, at least described, is the Materials Project, which is this open source database where you have known and predicted properties of 170,000 materials that the Berkeley National Lab, as well as other organizations, have been creating. And then further, there was a collaboration with DeepMind for their graph networks for materials exploration, which added some 380,000 more stable materials into that database. So my sense is one innovation from the kind of material science end is being able to make this database accessible with these predicted quantities to facilitate that educated guess step of the process. Am I understanding that correctly?
No, it's perfect. Yeah.
Okay. I know this isn't your specific domain, but anything that you would elaborate or add to that sort of like the novelty or the importance of having that kind of a database?
So people on the material science side, when they are investigating a material, they work a lot with the simulations, right? So this database would provide a lot of information on, sometimes you want to simulate that material in a certain condition, right? So you want to kind of test some properties. So what I see people here doing many times is they use the material as a base to try to see a possibility of what else they can do, maybe adding something or removing something. And this is what they do here. Like the theory side people, the theorists, they invest a lot of time, looking at these crystal structures. And I find amazing because I know nothing what's going on. I just see them, staring at the screen, rotating this crystal, and literally just pondering. You see them, they're not writing anything, they just ponder. So their minds can work, with the structure that is being simulated and get a lot of information from that. It's really cool how deep we got into this field of science where, and when I see them discussing about the materials, they know, how to phrase a sentence about changing specific one side of the structure to something, and then like everyone just agrees, oh yeah, that's right, and then I was like, well, that's really cool, right? I have no idea, but I like that. So it's very impressive on how they do this, first initial screening. They do simulations, they get energy levels, they get all of these properties, just analyzing, virtual data. And then many times it's just like, okay, this material is exactly what we need, but can we make it? And then that's when the job goes from the experimental side, from the theory side to the experimental side, where people are going to try to find a recipe to get there. So the lab, for example, is a lab that helps on this process to transition from the theory to the application side.
That's fascinating. As I'm imagining folks looking at these structures and trying to see what they might add into those structures, that almost feels like art in a way, or some sort of magical, experience. But I imagine there's a lot of, again, personal experience and maybe pattern recognition that they're drawing from that allows them to get that intuition for where to go.
That's right. That's how I believe it works in their brains. They have their own materials project in their mind, where they consult like, oh, I think we can try this. That's how I picture that they think. Because literally, I saw this many times. They stare at the screen, they rotate the crystal, and they're just like ponder. It's very interesting. That's not how I saw people work in other scientific fields before, when I was working with the wood science people.
The other thing that strikes me in that is, I think as a sort of a layperson entering this field, my sense is, well, if you can come up with some properties for material that you would want to make, of course you can just make it, right? Like we could make anything. It turns out that's not true. And I think the second layer of that, which I'm starting to learn, is that even for the things that we can make, if it requires some exotic, materials that are not easily accessible or accessible at scale, it almost doesn't matter that we can make it, because if you're trying to create, new blades for jet engines, you're going to need a lot of that material. And if it's super expensive or, not available in, areas that we have access to, then that's a non-starter as well, which adds, again, another layer of complexity. Cool. So, okay, so there's the sort of understanding and having an intuition for where we might want to, what ingredients we might want to assemble. Then there is the synthesis part of it, right? So making the materials, and it's time consuming, involves a lot of trial and error, and it seems like that's where the magic of your lab really shines, is in that synthesis. So I'm curious, could you maybe share a bit more about what synthesis looks like in your lab, and what was your innovation or breakthrough here, and how that happens?
So the DA lab is an autonomous lab that would work specifically with the high temperature synthesis. So because what we are working here is for energy storage, and these reactions, they happen in what we call solid state. So we just mix powders and then we bake them, and then all the calculations that the people do on the simulation side is to be sure that when the atoms react, they would go where we need them to go. So, but that's the hope, that nature is going to do what we want nature to do, right? That's not of course, what happens many times. So then changing parameters like the ramping curve the ramp curve of the heat, plus the time you keep on that temperature, the way you cool it down, and all of these are parameters that change how this material is going to behave. So one thing I learned that I found fascinating is the lab is not capable of doing that right now because of the safety of the robots. But when people are doing in the lab, they have these big tongs that they go and they take the crucible from the furnace, and like from 1,000 Celsius, they cool it down very quickly, because then the materials, when they cool down quickly, they tend to hold the properties that they had when they were in that high temperature. So no, there are these like secrets that the experimentalists have on the way they manufacture materials that try to hold the temperature. So the lab is very limited in many ways because we don't have the flexibility of a human doing things. But the lab would work 24/7 on the field that it can work, and that's where it helps a lot. So, but all of the reactions are exactly in this idea, like the high temperature synthesis, and then it goes from, we provide the material, we provide the target, the artificial intelligence models are going to look for similar structures that were manufactured this or that way. Then it's going to create an initial recipe on the ramp curve of the heat, and all these parameters. Then the powder station, the powder dosing is going to dose all these powders, mix them, then go to the furnace. Then the furnaces are automated, and the first part of my work here was to automate the doors of the furnaces, because we already had them. So there are some companies that make furnaces that their doors open automatically, but my first job here, because we already had the furnaces, was to automate them. So then what I did was just to use an Arduino and how do you call that one, linear actuator to open and close the door. So I had sensors here and there, that was my first job, to automate the furnaces. And then, because the communication with the furnace was already there, we could remotely control the temperature and monitor. But, opening and closing and putting samples inside, this is not part of the companies, at least at that time, were looking. I hope that now they are looking for, equipment that is exactly considering the need of this integration between robots and humans, that would help on that sense. So, well, that's basically what the lab does. And then on the synthesis. But then we have the characterization. So the lab only performs XRD, and basically takes these powders that sometimes would become a hard material, and then for the XRD they need to be in the powder form. So then we grind them, and then we place them on the disks, and then from the disks they go to the XRD machine. Then the data from the machine goes to the computer compares the data that's also obtained from the expected data, and then makes a decision on like, yes, I made it, no, I didn't. So what I can try here based on previous data. Wow. So that's the decision on the next recipe comes from this input, and then keeps going.
Wow. So it's really moving towards closing that loop and having that, autonomous cycle that you're describing.
Yes.
Yeah. Wow. So you said a couple of things that struck me. One is, you mentioned your North Star here, your mission really is around energy and identifying kind of maybe new materials for energy storage. So to put it maybe in layman's terms, right? We all have like lithium-ion batteries, right, in our phones, and I think EV cars use them as well. Are these the kind of sort of energy storage solutions that you guys are looking at?
No, we are moving away from that. So lithium has amazing properties in many senses, and I don't think the lithium batteries are going to disappear, next year. But we should move away because lithium is, flammable in air, and we have many cases of like batteries being on fire. It's a fire hazard, and I even know that in auto shops now, some of them are required to have like a place to, like, if the car is on fire, they put the whole car under the water.
Wow.
That's a safety precaution that it's being implemented because of the hazards, right? The batteries, they have a lot of energy. If this energy comes out quickly, too quickly, then it will be a problem. So what we have now that it's not probably, but I'm pretty sure this will be the next standard on batteries, are the disordered rock salt. Disordered rock salt is this material that is stable in air, and it doesn't catch fire. And I think the biggest advantage, but don't quote me on that because I'm not a material scientist, but the feeling I have about this material is that it has no liquids inside. So electrolytes are not necessary to make the material work like in lithium batteries. So just by removing the electrolyte, this liquid part, the battery becomes way lighter. So then you have what is very important for any transportation modality, that is the energy density. So these new materials that we are looking for today, they should be more stable, less hazards in many senses, more sustainable, but also with more energy density.
I imagine energy density is especially important for new applications if you want to do, for example, electric-powered flight, where
yes.
you get into this cycle, right, which is the larger the battery, the heavier the plane, the more power required to carry said battery, and so on and so forth. Lighter batteries will really help with that.
Yes.
And then safety being the other big aspect as well that you mentioned. Okay. I'm curious, so you mentioned there's this, you make the materials, you synthesize them, and then you characterize them with, XRD, make sure that we've made what we wanted to make. Is there a point in the process where and maybe this, again, I'm not thinking about this right, but where you see, okay, how much of a charge can this material hold? Like, what is the actual energy density of this, or does that happen at a later step?
So I think everything starts on the theory side still, because they know from the simulations how much energy can be stored in that material.
Oh, wow.
Yeah. So this is why they know that pursuing this, maybe not this material specifically, but this field of materials, all of them here will have similar properties, then that's how they know before even starting that that's a good shot to try.
Oh, wow. Okay.
So, and then later they have to test the material, because what we make in real life is not exactly how the perfect realm of the simulation, right? Where the material is perfect, there's nothing wrong with it, no gaps, no contaminations, but they intend to happen in real life. So then after manufacturing the material, they're going to test this material on cycles, usually since it's a battery, right? So they do the full charge and discharge cycles. And then they get the real information about the material that they could make and how close they are to the theoretical material. So
going back to your involvement in this, you mentioned your first project was, hey, we've got these furnace doors. We need to find a way to get these things to open automatically, I guess at the right time and close as well to get this process going. I'm curious, I've talked to a couple of folks now who work in the sort of automation space, and one of the challenges is kind of orchestrating all of these different robots and making sure that, robot A knows when to start its process and robot B doesn't start too early and so forth. How did you tackle that challenge yourself? Is there some larger orchestration mechanism? Is it sort of like robot or kind of device-based intelligence that's doing, you mentioned some sensors. How did you approach that?
So in our group here, we have the people working on the computational side. That's like I said, the theory on the materials, right? But we also have people in the A lab working more on the programming. So then our team developed this software called A Lab OS, which is the A Lab's orchestration software that is performing, the orchestration of the whole lab. So when we design new equipment, if it's like totally bespoke, so we made everything in home, we consider how this machine is going to communicate to tell the software, but the software is very flexible. So then we don't have to think too much on the software side beyond the, how I want my device, to tell the orchestration software, I am ready now, or no, I am on hold. These, I think, are the biggest constraints we have on that sense from the equipment development. But on the software side, it's very flexible, and I don't get too much into that. I couldn't help too much on that software, but the people working on that made a very complex software that facilitates a lot my work. This is why I didn't have to get too much into that, because all the complex part of this side, thinking on how I can have this module being available for a task, but this task is going to happen, in a different time. I can have many things happening at the same time because they're different equipment, right? Mm-hmm. So all the software, it evaluates the flow to try to get things going when they're not going to be a problem for another step. So I don't know how they made that. It's very, very magical to me because I don't deal with this high-level programming too much. I program more on the lower level, at least in some senses. I touch base with Python. I made Python solutions as well, but the level that they are working on that is something I am still not ready to dig into.
Okay, so it's complex, but the thing is they make it easy for you.
Oh, definitely.
And so they're orchestrating it. There's sort of a large, kind of intelligence that is looking at all these different instruments, and then you essentially give it the information that you need in order to tell you, hey, I'm ready, or this is when I'll be done, and then it's able to take that information and make sure that everybody else kind of is in sync with what your device is doing.
Yeah, and they published a paper on the A Lab OS. Oh. So the paper and the software are available, and their idea was to provide the A Lab OS software to the community. Even though it's like our software, their goal is to make it public so then other people can go and start their own labs without having to think too much about this.
Oh, I love that. Okay, cool. So they're making it open source and making it available.
Open source.
That's so cool. So you started off, your first sort of big task was around orchestrating or getting the furnace doors working appropriately. What did that lead to up to today?
So then, I think in the beginning, before we had more equipment, some things were very clear on what everyone was doing. Then later, when the lab was getting, shaped and many things start to be, to start to work, then the job became more, harder to separate exactly what everyone is doing. So when we had, for example, any meeting about like how to develop this machine here, we would have brainstorm sessions, and then everyone is going together, giving their input, and it's harder to say like after the doors what exactly David did or what Bernard or Yixing. There are things, of course, very clear what everyone did, but there is a moment where it's just like, well, it's not me, it's the team. So we can say clearly that the A Lab is the work of a team, because it's like our, I can't remember the word for that, but what's a good word? Sorry for that. But what is a good word when people have this cohesion, when they really work as a team together?
Yeah, I mean, I almost was thinking of the idea of flow. Like there's a sense of, I know people have a sense of personal flow when they're, working on something and really focused, and they almost lose a sense of time and space and so forth because they're just in it. It almost sounds like your team achieved this sense of flow, because you're like, after this furnace door, we were all just working and sort of building this thing cohesively together.
Yes, that's true.
Yeah.
The collaboration level in the A Lab is like the whole team is very nice. So I think when we consider an interview for a new person, a postdoc or a student to come to the group, I think one of the things we think the most is like, is this person going to join us in the same level of, collaboration? Is this person going to join, the A Lab is a team. It's not me in the A Lab, but it's us. Mm-hmm. So that's a feeling that I believe that everyone in the Lab has. That is just like, it's truly collaboration. It's the most collaborative work I ever did in my life. And it's very, very nice. Because I think this is probably the secret why we could go so far. Because let's take, for example, a vacation. When we consider vacation, we tend to consider, like my needs, because I'm going to have a vacation. But then I know that like my team is going to need me, so I can consider some things, to go around it. It's not, I'm not talking about being workaholic, but just like, my team needs me, and I need my team as well. So it's important to consider, that maybe 1 week after might be a big change for the whole team. So I should consider that. But whenever I talk about like, I'm going to go to vacation and this is what I plan, people always tend to tell me like, no, it's all good, you can go, don't worry about this. But I think everyone in the back of their mind keep like, no, I have to wonder, I have to ponder, because that's how the whole team thinks. That's the feeling I have. And everyone that came and left in this time that I'm here, these 3 years, I think everyone had the same profile on understanding that a team is a team. That was really cool.
It almost sounds like there's a level of orchestration that's happening, not just for the robots, but for the team itself.
I agree, yes.
Yeah. I'm curious, so, you're, to kind of dive a little bit more into the way in which you work. So the A Lab, I think, is interesting in that it sits within, the Lawrence Berkeley National Lab, but the lab itself is also managed by UC Berkeley. So there's a university and sort of government kind of relationship here. I'm curious, like, how does that structure impact how collaborative this organization is? Access to resources and funding for folks who haven't worked in this kind of environment before?
So they are different institutions. Like many people believe that because they are so intertwined, right? So the lab is here, the university is right there, just go down the hill. So people believe that they are the same institution, but they are totally not. And there are, for example, I don't have access to the university, for example, and people from the university don't have access to the lab just by using their badges. but any student that wants to perform work in the lab, let's say for example to use a user facility, they just have to write a proposal with their professors. They submit the proposal. If the lab believes that's a good use of their resources, the students can come and do part of their research here. So that's how I've met personally many students doing that. Also, in the A Lab team, we hired many students already to do some internships with us. And these interns usually, they not only material science. So we had people from mechanical engineering coming, computer science coming, and of course material science. And all of them did a great job with us. And I'm specifically talking about just the A-Lab people. So then we are very thankful for this collaboration, because I think they do the best that they can to make it to be as smooth as possible. It's really cool.
So it sounds like it's not an open door policy where anybody can wander in, but it's almost like there's a screen door policy where if you apply and you get approval, you can actually come if you're at Berkeley, at the university, to be able to come here and collaborate, and there's internship opportunities available and so forth.
That's right. And even the ALS, for example, is a good example on that, because people come from many places.
What is the ALS?
Oh, yeah. It's the Advanced Light Source, which is they use the same building as the original cyclotron, but the cyclotron is a different building now. So this is another type of technology on the particle acceleration side. And the ALS is a place where people from everywhere in the planet, they can apply the same idea for a grant. And but when I say grant, people tend to think about money. So let me say that as far as I know, if your proposal is good, they're not going to charge you to come here and do your experiments. You just have to bring your materials. They do all the clearance, the safety, the how do you call it, the closed door policy?
Oh yeah, the closed door, screen door. Yeah,
yeah, the screen door. Yeah, they have to do a screening, right? Yeah. But once people are authorized to come, they will bring their samples. They're going to do their analysis, get their data, and I think this is a very good way that they are spreading the impact, because it goes beyond just like California or just US. Science is a field that they try to have it should be that way on the collaboration side, right? So they try to be very collaborative, and as long as your project is good, they are doing their part to sponsor it as well, at least on the data collection.
So you mentioned impact. Maybe taking a step back, what inspired the vision of the A-Lab in the first place?
So I believe my boss, Professor Sider, would reply to this question much better than me. But I know that he's working with the materials for energy storage since the 90s. And he's one of the biggest specialists in energy storage. So I think there is this tendency on many fields on trying to automate everything, automate as maximum as possible. So, and that's great, because I work with automation. I defend that idea. If we can automate, we should. That's something I'm always saying. So I think that feeling, was just natural on looking all this, hard part that's in the lab, because people, it's so much time that's necessary for you to go and get from, the synthesis, it's a long process. So you need to take the material, weight the material, then you need to mix the proper way. So it's a long of small processes that you need to do your own orchestration on a different work, because sometimes you need to leave the machine for 2 hours. Then you have to come back for a different step. So you have to rearrange everything. And when you have automation helping you with that, then we can have people doing things that only people can do. So I think it's a natural course. But for you to be able to convince, the stakeholders that you are the person to receive that money, that's the hard part. And I think he was a visionary on trying to not only automate the synthesis, but to integrate the synthesis, the characterization, and closing the loop with the decision-making algorithms, So bringing all of this together was a great achievement, and I'm very glad to be part of it. But
go ahead.
No, it's just I don't know where the idea came from, but I love it.
If the A Lab achieves its goals, like what do you think the impact will be of being able to automate this material science discovery process?
So one thing I know is that there are other labs already inspired by the A Lab, and I believe that the principles that we are using in material science can be transferred to other sciences as well, because the A Lab actually follows one thing that we see in biology already, right? So the biological field is already so automated. So I believe that that's one thing that's going to happen. The material science is going to become in the same level of automation. And in my perspective, all scientific fields are going to follow this trend, because we need more materials, right? We need better materials for storage, but we also need better tools, for example, for vaccines like we had on COVID time. And having this automation was so important at that time. So I believe that one day when people have, maybe people are talking about energy crisis that's going to come, new materials can help to overcome that. And sustainability, all fields. So I think material science spreads in many ways, the same way as biology is just everywhere. So I see that happening in the future, a future where materials are, made faster, better, and we have less gap between what is made by science and what is actually available for, people go and buy off the shelf. So I think these labs are going to provide more of what is a result from science into actually, something you can go and have in your home, either a product or maybe just knowledge that can help you on your daily life.
So you mentioned, the success of this one means that, material science is going to essentially maybe get closer to where life sciences is today in terms of how deeply integrated automation is. And it also opens up all sorts of new, possibilities for materials, from energy to sustainability and so forth. I'm seeing, which I think is exciting, like a lot of investment from even like the VC space into startups who are trying to push them, the ball forward. So there's organizations like Schrödinger, which I think is focused more on the kind of pure play simulation side of the house, to Venture Studio flagship Pioneering, which recently announced, I think, Lila Sciences, and they're seeming to do a big push in autonomous materials discovery. What do you make of this? It seems like new excitement in specifically automating material science.
Well, I think this is really good in all spheres you can imagine. But from coming from a different science and entering into material science and seeing the importance of all these discoveries, this is very exciting. I get inspired by it, and there are many projects that I see that many times I wonder, like, oh, I would love to work with that. It sparks curiosity, and many times when I read texts or articles about this, people pursuing such an important technology, or something that might be, once they finish that discovery, it's going to be groundbreaking. And then I think things like, oh, what a great time to be alive. And the other thing is how they're doing that. It sparks a lot of curiosity on like, how are they looking at this and trying to get what they are looking for from that specific and such a complex thing to do. And that brings a lot of curiosity too. So, but from the impact that's going to have in the future, I see that this is great things are coming, and I'm very happy to see this due to many issues that are happening, climate change and all this stuff. I love to see how many people are engaged in trying to bring solutions that are not going to limit us. Actually, it's the opposite. We are protecting the environment while having something that's going to help our lives. That is great.
Well, it certainly sounds like, for you specifically and for folks who are interested in the intersection of automation and materials, like the future is bright, and there's going to be more and more opportunities to be able to really dive in and do this work. Going back to your own specific work, you started off with, this task around the furnace doors. You then moved into, deep team-based flow for a couple of years. I'm curious, when we were talking before we started shooting, you had mentioned this, I think, new work you're doing in the microscopy space. So can you tell us more about why that's interesting to you and what you're excited about with microscopy?
So one of the reasons why we need microscopy is because microscopy is in the field of characterization, right? So we can look further away and just understand the shape of the materials and the morphology. But then we can go deeper and get the composition. So we can know, for example, maybe in a broader XRD, I don't see the material I'm looking for because I need to make a lot of this material to be able to understand. The machine is able to sense that material is there. But once I can go specifically to one crystal and pinpoint like, what is exactly here? Aha, I made it. So, the microscopy helps greatly. And that's how, but this all came later once people, so basically the A Lab was going, I'm going back and forth, I'm sorry.
That's fine.
So let me try to start from the start. So because of the importance of characterization that is brought from microscopy, on this sense that from a further perspective you can get the morphology, but you can also do analysis of what is the composition of the material. And if you go really close, you can even pinpoint like the way they're connecting to each other and get a lot of information from, from, for example, transmission electron microscope can go and show you, basically the atoms. And then you can see the crystal structure in a sense that other microscopies can't. So the microscopy is going to be the next step of the A Lab. So we are going now from one characterization to bringing one more. And then for sure you can imagine that more ones are going to come in the future too. But for now, the project is focusing on microscopy. Then the task that was given to me was like, how we are going to take this material that comes from this powder form from the A Lab into the microscope. And then powder, it's very messy. And how to do that without contamination, how to do that without creating issues for the people working in the lab, right? The lab is safer than other labs because we don't need people inside all the time, but from time to time we need people there. And we also need this environment to be safe. So how to do this all? I can't just go and blow air and hope that the air goes exactly where I need, right? So I need to have a method on how to collect this powder and place it on the sample holder. But not just that. I also need to have the right amount of material and the right space between it. And many times in the A Lab, I don't have the biggest control on the particle size, and the smaller the better. So all of these constraints, when you give your example on like, what are the requirements? So I had to go and talk to the experimentalist and ask them, how is a good sample in this sense? Is this that I prepared a good sample or a bad sample? So I could gather feedback, and then later I came up with the machine that the lab is patenting right now that is going to provide this transition between taking the powder from the A-lab and putting inside the microscope and then analyzing this material. So the device I made makes this bridge, and it's what is going to transport the materials and allow an automatic microscopy analysis.
Wow. What sounds like such a simple task, which is, hey, just analyze this with a microscope. Once you start to bring into the equation of, gosh, what is a good sample? How do we do this in a way that doesn't harm humans and create a polluting environment? I can see just the incredible complexity. And then to automate that, right, and to give some system intelligence to be able to think through all of those. Very exciting. Well, we've been talking a lot about the A-Lab. We're also steps away from it. Would you be up for doing a quick tour?
Oh yeah, let's go.
Yeah, all right, let's make it happen. Awesome, well here we are in the A-Lab. David, thanks for having us. Show us around. What are we looking at?
All right, so here, this is the computer where everything starts. So you come here, for example, to go and set what is in the dosing head. So the materials you're going to use for your synthesis. Then in this computer, you can also go and set the experiment you're going to run. So everything starts here. So you submit your experimental data here. Then once the computer receives your experiment, it's going to do the stoichiometry reaction and see for the recipe how much you need of each material. Then we go to the powder dosing station, where this robot arm here takes from the bottles there, and from each bottle puts in the balance, doses, everything inside one of the plastic containers that are in the background I will show you very soon. So after everything is dosed, it goes to the ethanol dispensing station, that one, and dispenses the ethanol inside the container. Then puts the lid back on the container and brings to this central machine here, which is the speed mixer. So then everything is mixed. Then they come here to this station that does the removal of this liquid and place inside of the ceramic crucible. Then the materials are now in a liquid form, right? We need them to be dry. Then they would go to this drying station here that dries all the ethanol. And then from here they go to this circular structure. There's the one you use at home, I forgot the name.
Like a dolly maybe?
Yeah.
Yeah.
So then this one here is what is the connection between you and the machine, or between the robots, right? So then from here, they come to this window where that robot arm would come and pick crucible by crucible and bring to the ceramic racks there, and they go inside the furnaces.
Wow.
So then we can do up to 8 samples at a time.
So these are the famous furnace doors?
Yes, these are the yes, they're the ones. So then they go inside the furnace. We can do reactions in air here, and we can do reactions that are not in air on these furnaces that are on the floor. They are tube furnaces. So we can control the environment, the atmosphere, for example, by using this for like argon, oxygen, or nitrogen. So then from here, after the reaction is performed, we have to take the sample and then do the analysis. So then now we go to the other side again to do the, to show you DASH, the powder recovery. So, and then here in this station is where we have, after they are baked, they would go back to the trays there. And then this robot arm here is going to take from the crucible, bring the crucible to the ball dispenser, which is right there, the tower. So as you can see, like a lot of 3D printed parts. So this lab here was designed, the powder station, was designed by a company up from our request. But then this side here is like us. We made this part. And then we have here, for example, the crucible receives the ceramic ball from that tower, then goes to the shaker. The shaker right there is where the crucible is going to be, shaking this ball inside to grind this material. And then after it is totally ground, we dispense in one of the plastic containers. And then the plastic containers are going to be, they need to have their cap changed. So some caps, they have sieves, and that's how we dose the powder onto the disc. And the XRD disc later is what goes to the XRD machine.
Those are the XRD discs right there on the
back
panel? Okay. And
they go
discs.
here.
Okay.
Yes. And then from here the data is obtained, and then they go back to the computer and the cycle continues.
We've come full circle.
Yes.
This is incredible. Wow. Okay, so a couple questions for you. Let's back up. So we start off with this machine, as you said, moving into this unit here.
Yes.
One of the things I noticed is there's a big old Mitsubishi logo on this robot arm.
Yeah.
You mentioned that some of these, I guess, pieces of equipment you've manufactured or made, others are kind of purchased. I'm curious, like how easy or difficult do these different vendors make it for you to be able to put these materials or put these robots together, orchestrate them through this robot software that you talked about?
The vendors are amazing. We never had any issue. They actually do a great job on everything. So whenever we need support, they're always there. So I never had any. I mean, since I'm here, we never had any issue that I can recall on anything. And then Labman, for example, that made this for us, they understood the assignment. And as you can see, this look amazing. So of course we would like everything to look this way, but the lab is growing, right? So then we have many. For example, another example I can give is the tube furnace itself. So MTI made that tube furnaces for us. So we said we need something like this, and then they're like, okay, challenge accepted. Then later they got the tube furnaces for us. And I think, like I mentioned before, some companies are trying to manage this need that is, we need the equipment to work and do the job, but we need to go beyond that. I think the standard very soon will be on all the equipment having at least some automation level. Maybe the equipment is not automated to do the whole work, but could be just, for example, the robot arm doing something. So speed mixer, for example, didn't make this fully autonomous by standard, but in this situation here, this machine works with the whole software that Labman made to make this flow work well.
So it sounds like it's a really collaborative process with the vendors where you're giving them your requirements. And they're saying challenge accepted.
Yes.
Are they actually coming into this space and looking around and looking at dimensions and
many times?
Yeah.
So people from Universal Robots came. I'm pretty sure they're from Universal Robots, but some people from the robotic arm vendors, they came to visit us, and in the university where we are expanding the A lab. There, they are even providing training for us because we have this mobile robot. And we need to learn how to use it. So they came to, and the experience is always great. It's very nice. I think engineers go well together.
So then you've got these containers. What did you call the name of? Is it crucibles here?
Yeah, the crucible is the ceramic one.
Okay, the ceramic one's right there.
The plastic one is the vial one.
Okay. And then you have in those...
the bottles?
The bottles. Those are the different... Is it powders that you have?
Yeah, so every single one of them are different materials. Sometimes we have, like, if we need a lot of one material, we can just have more of that material in more than one bottle. But I think that only happened once.
So there's also really an inventory thing that you are having to manage as well, which is making sure that you have, as these computers maybe have different hypotheses for what they want to be creating, you need to make sure that there's ample supply of that.
Yes.
Okay. Is there, I guess, how much of this material do they go through in a typical run?
Oh, no, it's not a lot. So DA Lab makes very small amounts, right? So you're working on like 1 gram, 1.5, 0.8 grams. So we usually make like a few amount of materials per run. So it's not, they last a good time.
Well, you mentioned the furnace doors. I want to, again, check out your masterpiece here that you, that you were
The very
developing.
initial one. Yeah, you can come closer here.
Okay.
So the robot's paused, so it's safe to come.
Okay, cool.
So yeah, it's very basic. It's just an aluminum structure, this case, a sensor here for the door. There's already a sensor inside this linear actuator that turns it off automatically when retracting. And the reason why we stop in between with the sensor is because even though there's a sensor to stop it when it's fully extended, we are not fully extending. We have to stop in between. And then we have this safety pin here. And if someone needs to open this, they can just pull the pin and open the door immediately for any safety concerns. And then we have this aluminum extruded structure to just go around. So it's a very cheap structure, that then we have the controller there, the black boxes. That's each box control, 2 of them, and it's working since from the very beginning. So it never failed. So we are aiming, now with the expansion of the lab to have more of the electronics being on PLCs, and this one is still on an Arduino. But for 3 years, 2.5, let's say, everything is working really well.
What are PLCs and what's the advantage of moving to them?
So PLC is a programmable logic computer, and they are the industrial standard for these applications where you need to control machines, right? So they are very robust. Their time on acting upon sensors, for example, not many, I'm pretty sure all of the safety that's regarding, like, for example, an elevator, all the sensors on the door to keep people protected are from PLCs. So it's and then we have different tiers. So here we're using only the very basic automation ones, but for some applications you need to have the safety level ones. So fire extinguisher systems, they always are based on PLCs as well. So many of these industrial applications, when they touch the automation side, the PLC is what brings that. So you can connect to this unit all the sensors and the actuators, and then you have this software that never basically breaks. It runs constantly, thousands per time per second. They are analyzing the sensor, So I think an Arduino can analyze a sensor 16,000 times per second is the time you can analyze a sensor or an input. That's the time that the clock of the processor. And then the actions are based on this speed. This is why things are so fast. And then you can have the safety devices that their clock speed is way higher. So then we can trust that these machines are actually protecting our lives around these strong motors. Imagine the size of the motor to move an elevator, right? You don't want that motor not being controlled by something, that is not very fast to know, immediately that something is wrong.
Wow. I notice you have 4 furnaces here. Tell me about the need for 4, and how does that relate with, I guess my natural question is, are there multiple basically flows happening at the same time, where as something is baking, you can create another experiment and have a lot of parallel processing?
Yes, definitely. This is what happens. So I can have one batch coming in, and then the A-Lab OS even analyzes if, for example, let's say you have a reaction, and then some other scientist comes with a different reaction, and sees that the temperature of the furnace will be the same for both of you, and the profile is the same. So then this software is going to try to combine your samples with the samples from the other scientist.
That is so smart.
It's really cool. So all these tasks happen at the same time. And the process, of course, are parallel. So I can have new samples being prepared while I'm recovering the powder here to prepare for the analysis, while other ones are being analyzed right now. So it keeps going. So we can have people constantly having new experiments being inserted, and the lab is going to manage everything, calling us from time to time just to clean some things.
That's amazing.
So, and the question about 4 furnaces, right? It's because we can only have 4. If we had more space, we'd have more than 4. That's for sure.
There we go. There we go. So, donors, I hope you're listening. Open up those checkbooks. Let's create a larger space here.
That's right.
And have more than 4. Amazing.
We want to expand the lab as maximum as possible.
Yeah. Awesome. Well, on that note, one thing I like to ask in every one of these interviews is, what's one way for folks who are listening, whether they're policymakers, investors, other engineers, maybe, fresh talent, what's one way in which they can be helpful to you and to the lab?
So I think the vendors, like I said before, should consider bringing some degree of automation, or making their machines, capable of being automated more easily, or more integrated more easily, I would say. Many things already have software inside. And then sensors sometimes are not that expensive. So having more solutions that are thought that the automation is necessary. It's not just a perk that some people are going to need. I believe that the trend is the more people automate their products and help on the sense of these, to try to bring automation to all fields, right? So the more the companies think about that when they develop their solutions, the better it's going to be for science in general, for industries in general, and I think that's the new standard. So I think that's one of the things people can help us. More things, I think the society needs to monitor what science is doing, and try to be more involved on where science is going, because many of the projects that are supported by the society needs. So when we see as society that some things are necessary, then the need will push the investments that way. So the more we have collaboration from everyone, the more science is going to be relevant and doing work that is actually solving the problems we have now, and in preparation for problems that we see that are being developed. So it shouldn't have a gap between what we do and what's available for the society. That's the ideal, right? But that can only happen when everyone do their part, and we need the society to participate on that, So even just by being inspired, and then preparing the next generation of engineers to think about, wait, we have to go that way. So then prepare, a whole batch of new engineers that are going to think and go that way.
Awesome. So vendors, automation out of the box, society, if we want better EV batteries, safer batteries, if we want new materials, it doesn't just happen. There's a lot of, as we can see, as we look around the lab, complexity and talented people that need to come together and work seamlessly in order to realize them. So make your voices heard, make sure that groups like the A-Lab are getting the kind of support that make the future possible.
That's right.
Awesome. Well, thank you so much, David. I'm going to see if I can do a selfie here. There we go. All right. Well, thank you, David, for this time that we had together. Really grateful for you inviting me into your space, and looking forward to following all of the adventures that you have ahead of you.
Oh, thank you.
Absolutely.
Very happy to have you here.
All right. Take care. Bye.
Bye-bye.